Hello everyone. We are starting the new video series for our subject EC402 Nanoelectronics, and in this video series we shall cover some important topics in our module 5. So this is the first session of our video series, and let's see what are the main contents or the syllabus of module 5. So in this module we shall basically cover the transport mechanism in nanostructures. So the transport mechanism may be under the effect of an electric field, we shall see that, and as a result what are the different type of transport mechanism that is generated. The parallel transport, perpendicular transport, the hot electron effect, so on. We shall also see the quantum transport in nanostructures and the Coulomb blockade effect. Later we shall discuss the transport mechanism in nanostructures under the effect of a magnetic field. There we will observe the behavior of a crystal under a magnetic field, as well as some very common and very important effects. So basically for this module I have referred the textbook Nanotechnology for Microelectronics and Optoelectronics by J.M. Martinez Duarte, and the chapters 6 and 7 will do the job. So let's begin. Before we start our module, let's have a quick recap of what we have learned so far. So we have completed 4 modules, and in the 4 modules we began with the mesoscopic physics which was governing the nanostructures. We saw the quantum nature of nanostructures, the de Broglie wavelength, various characteristic length, the Schrodinger equations. We discussed all these things. Later we went on to the different types of nanostructures. We have the 1D, 2D, 3D, zero-dimensional nanostructures. We discussed their properties. And in the second module, we covered the fabrication methods of nanolayers as well as nanoparticles. We had a number of fabrication techniques for nanolayers and nanoparticles. And later, in the third module, we focused on the characterization schemes. We had a number of characterization schemes for analyzing the physical as well as the chemical properties of a nanomaterial. So we discussed that. And finally, in the fourth module, we focused basically on the two-dimensional electronic systems. We had the quantum wells, multiple quantum wells, modulation doped quantum wells, then the superlattice. The concept behind superlattice was pretty important. We had a beautiful analysis of that, and that's where we stopped our session. So to continue from there, in this module we shall basically see the transport mechanism, right? So in this session, the first session, we'll deal with the electric field transport mechanism of nanoparticles, right? Okay, so the electric field transport, how does the electrons in nanostructures move under the influence of a electric field? That's what we are going to discuss here in this session, right? Okay, so we are like well familiar with the quantum wells, the concept of quantum wells, and we have one of our favorite exams, right? Of the modulation doped heterojunctions. We have gallium arsenide and aluminum gallium arsenide quantum wells formation. We have discussed that. Now we have seen that when semiconductors of different band gaps join at the interface, we get a quantum well. Now what happens is the behavior of our electrons in this quantum well, when their motion is parallel to the interface, we have this quantum well. When their motion is parallel to the interface, we call that kind of transport as parallel transport. Now, are we familiar with parallel transport? I would say yes, because parallel transport is nothing but the normal electron motion in a normal 3D bulk semiconductors, except that there is a difference in their DOS, which is the density of state function, as well as the electron scattering mechanism. So a parallel transport is nothing but the normal electron motion in a bulk semiconductor. The difference arises in the DOS function as well as the scattering mechanism, electron scattering mechanism. That is one type of transport under the influence of an electric field, the parallel transport. Now, apart from the parallel transport, we have another kind of transport called the perpendicular transport, and which we can at least guess from the name that when the electron travels in a direction which is perpendicular to your interface or perpendicular to your potential barrier, this is called perpendicular transport. Perpendicular transport. So when your electron motion is parallel to the interface, you have parallel transport, and when your electron transport is perpendicular to your interface, or when your electron transport is through the potential barrier, you have perpendicular transport. Now, here the perpendicular transport is like completely different from that of the bulk materials. We can't expect perpendicular transport to be same as that happens in bulk materials, because in perpendicular transport in nanostructures, normally the transport mechanism is based on tunneling effect. So so in this session we shall deal with parallel transport alone. So we have seen that parallel transport is the movement of electrons parallel to the interface. So make that very clear. Now, initially this parallel transport was observed in MOSFETs, and later this was utilized for our MODFETs too, or the modulation doped heterojunction quantum structures. So what was the specialty of both these structures was that electron motion occurred in a region where we don't have any kind of charged dopants. If you recollect, in MOSFET the electron motion was through the channel, right, or the inversion layer. So where we don't have any charged particles or charged dopants present, because that's basically the substrate. And coming to the MODFET, MODFET is nothing but our modulation doped heterostructure, right, which we have formed from a gallium arsenide as well as aluminum gallium arsenide structure. So this is nothing but a modulation doped heterojunction, right. So when I say MODFET, let that image come to your mind. Fine. So again, coming back to MODFET, the electron motion is taking place in the gallium arsenide region, which is again not doped. It is an intrinsic gallium arsenide. So again, that region is free of charged dopants. So due to this property itself, the electrons can reach very high mobilities because they don't have any charged dopants to stop their transport. Now, parallel transport is similar to the transport in bulk semiconductors. We have seen that, right? We have just discussed that. Now, what we have to consider in the case of parallel transport in nanostructure is that we have additional scattering mechanism. And now we are not dealing with bulk semiconductors. We are dealing with low dimensional system, and that is very important. So let's see the electron scattering mechanism that happens in our nanostructures. So basically the main scattering in nanostructures is due to phonons, impurities, or even surface roughness. Now what is phonon? That's a question. Like we are familiar with photon, right? It's just nothing but a quantum of light. Similarly, phonon is nothing but a quantum of lattice vibration. They are similar to photons, right? But phonon is lattice vibration. A quantum of lattice vibration is called a phonon, and they carry heat in the material. Now, due to the presence of phonon, impurities, surface roughness, we have different type of scattering mechanism, such as the electron phonon scattering, impurity scattering, surface roughness scattering, and inter-subband scattering. So, we shall see in detail each of the scattering mechanisms. To begin with, the electron-phonon scattering. Well, the electron-phonon interaction, we can observe it in most of the materials. There is no specific material to observe this. It is very common. It is a common kind of scattering. Now, how does the scattering occur? So, see, in room temperature, basically our lattice of material is not very it's not constant, right? They continuously, since the atoms are continuously vibrating, the lattice of the materials also keep vibrating about their mean position. So whatever be their position, they are vibrating along their position, and this vibration can increase the temperature, and this can thereby cause the generation of phonons. Okay, so we have our atomic lattice, or we have the lattice of our structure, and at room temperature itself the lattice is not constant. The lattice keeps vibrating along its mean position. Due to this vibration, of course, when there is a continuous motion, due to this motion there is a development of temperature, and this temperature and this lattice vibration will cause the generation of phonons. Now, once these phonons are generated, we already have the electrons, right? We already have the electrons which are moving. These electrons will have an opportunity to collide with the vibrating lattice. Thus, we have the electron-phonon interaction and the electron-phonon scattering. I hope that is clear. Okay. So the phonon scattering, the electron-phonon scattering mechanism is like we can observe it when your temperature is greater than 50 Kelvin. Now, in the case of narrow quantum wells, when the width of your quantum well is too small, the phonon momentum may not be conserved, and as a result, what happens? Now, when there is an uncertainty in the momentum, the number of electron-phonon scattering also increases. When you particularly don't know the momentum of your phonon, the electron-phonon scattering also increases. And thus, and because of this reason, the phonon scattering becomes like very strong in low dimensional structures when your temperature is greater than 50 Kelvin. But in the case of bulk semiconductors, the phonons have well-defined momentum. We don't have an uncertainty in momentum for bulk semiconductors. So this is one important difference, right? In the case of nanostructures, the momentum of phonons are not very certain. You can't be certain about it, and because of which the electron-phonon scattering is very high. But in the case of bulk, the phonons have very well defined momentum, right? So that's about electron-phonon scattering. Here we have seen what is phonon, how does this electron-phonon scattering occurs, and how it is different from the bulk semiconductors. I hope these many points are clear to you. The second scattering mechanism is nothing but the impurity scattering. So as the name suggests, it's a scattering due to the presence of impurities. Now your impurities may be ionized impurities or neutral impurities. So both these ionized as well as the neutral impurities, they form a large contribution in scattering in semiconductors at lower temperature. Now consider our very familiar modulation doped heterostructure, the aluminum gallium arsenide and the gallium arsenide region. So here we can see that the electron motion occurs in this region, right? In this region, which is the gallium arsenide region. Or the electron motion is parallel to the interface, right? Similarly, in a Mohs structure also, the electron moves within this inversion layer. We have this inversion layer or the channel region here, and the electron motion occurs in this. And here the electrons are separated from the impurities. Where does the impurity lie? In the silicon oxide, the gate oxide layer. So basically we are trying to separate our electrons from the impurities present in our materials, right? So that's what we are saying here, right? Now what happens, what are the things that we must consider when we want to calculate the impurity scattering in MOSFET? So let's see what are the things that we'll consider while doing that. So while determining the impurity scattering in MOSFET, we take into consideration certain assumptions, which are, we assume that the impurities are located in a 2D plane at a distance d of the electrons in the channel, and the electrons that cause scattering event has energy close to Fermi level. See, as we have said in the case of our gallium arsenide, aluminum gallium arsenide layer, we had made sure that our electrons in the channel, they have an energy close to the Fermi level, right? And the impurities are located at a distance, at a particular distance away from these electrons, so that the scattering event has an energy which is close to the Fermi level. So that is one assumption. Another thing that we assume is that the concentration of the impurities must not be too high. So why do we consider this? So that the charged impurity interacts independently with the carrier or the electrons. So we don't want the impurity concentration to be too high so that their interaction is all mixed up, say. So with these two assumptions, we can determine the impurity scattering in the case of a MOSFET. See, when I repeat MOSFET, it is nothing but aluminum gallium arsenide and gallium arsenide modulation doped heterojunction or heterostructure. Okay, so keeping these assumptions in mind, we can find that the mobility of carriers in the case of a MOSFET increases as d cube. It's d cube. So, and what is d? If you remember, d is nothing but the periodicity of the well. The width of the well plus the barrier together forms your periodicity d. Now, with what regard can we select a value for d? In fact, there is no particular or a perfect value for d. If the value of d is too large, the concentration of electrons in the channel decreases. We can just visualize that, right? See, if the width of your well is too large, which means your periodicity is too large, the electrons may be present anywhere in the channel and the concentration of electron automatically decreases. When the concentration of electron decreases in the channel, this in fact in turn decreases the electric field and thus the transconductance of a MOSFET. So in impurity scattering, what we have seen is that what are the type of impurities that cause the scattering? We have the ionized and neutral impurities, and we saw the case of modulation doped heterojunction and MOSFET. Where is the presence of electrons, right? So then we discussed what are the assumptions that we can consider to determine the impurity scattering for MOSFET. So we considered two assumptions for that. That was done. So I hope the two scattering mechanisms, the electron phonon scattering and the impurity scattering is pretty clear. Moving on to the third kind of scattering, the surface roughness scattering. Now, again we can interpret from the heading that it is some kind of scattering which may be formed due to the roughness in the surface, right? That's pretty clear. Now, where is this kind of scattering prominent? That's what we are going to see. Now, This kind of scattering is basically due to the interaction of electrons with rough surfaces. We may not always obtain ideal flat surfaces. Surfaces, when I say, it's like interfaces, right? So the interface may have some kind of roughness. Now, let's consider the MOS as well as the MOSFET. Now, in case of MOSFET, this kind of scattering is not very prominent. Why? Because MOSFET basically have perfect interfaces. We have seen various techniques for manufacturing MOSFETs, right? So basically we have this MBE, a molecular beam epitaxy method of fabrication of MOSFETs. So these methods are so precise that the interfaces formed from these methods form perfect interfaces. We don't have any scope for roughness in the case of MOSFET. But that is not the case of most devices. In most devices, see what happens, we have an oxide layer, right? This oxide layer is in fact grown thermally. It's not like we can make it perfectly using MB. We can't do that. So in most structures, this oxide layer is grown thermally. And as a result, your interface is not as perfect. We have roughness in the case of most structures. It's not, the interface is not perfect in the case of, as in the case of MOSFET. Now, we can see that in the case of most structures, the interface scattering depends upon the width of your quantum well, right? Now, as the width decreases, the electron wave function, they penetrate deeper into the oxide semiconductor barrier. As the width decreases, the electron wave function, they can penetrate deeper into your oxide semiconductor barrier. And what happens as a result? As a result, as the wave functions penetrate deeper, more electrons are exposed to your interface roughness, because of which your scattering increases. And it is the reason, and this is the reason for the decrease in mobility. Why you can find a decrease in mobility at a particular gate voltage. So the impurity scattering is basically significant at temperature low enough so that your phonon scattering is negligible. So like both of them doesn't happen at the same time. When a temperature is so low that the phonon scattering is negligible, we have a scope for surface roughness scattering. That's about surface roughness scattering. So in surface roughness scattering, what we saw is that as the name indicated, the scattering was due to the surface roughness. Here, there are two devices that we consider, the MOSFET and the MOS structures. In MOSFET, this kind of scattering is like negligible, since their interfaces are perfectly made using techniques like MB. But that's not the case of MOS structures, where the oxide layers are grown thermally and hence they have more surface roughness, right? So, that's all about surface roughness scattering. I hope that's clear. Coming to the last scattering mechanism, the inter-subband scattering. So for that, I want you to consider, before we go on to this, I want you to consider this figure. So now just consider a 2D electron system. We consider potential well, say. We have quantized energy levels E1, E2, E3, and we have the corresponding subbands just as shown in here. So, say when your electron concentration is very large in the well, the energy level with energy greater than E1, energy level with greater than E1 will obviously get filled because your electron concentration is pretty high. Now, if the electron concentration is high enough so that your Fermi level just crosses your energy level corresponding to E2. When your electron concentration is high so that your Fermi level crosses your energy level E2, what happens? The electron with energy near to your Fermi level, because it has crossed E2, near to your Fermi level can undergo two types of scattering. Either it can go an intra-band scattering within the energy level E2, intra-band within the same section, or else there can be a interband scattering between n equal to 2 energy level and n equal to 1 energy level. Okay. So what have we seen right now? We have a 2D electron system, or simply saying it's a potential well. When your electron concentration is too high, such that the energy level greater than E1 gets easily filled. Now if your electron concentration further increases so that your Fermi level just cross E2, there can be two types of scattering. One is an intra-band scattering within the subband E2. Another one is the interband scattering along your energy levels n equal to 1 and n equal to 2 across these two levels. This kind of scattering mechanism is called inter-subband scattering. Right? So in this case, the total scattering probability increases and the mobility, electron mobility, decreases. I hope these four kinds of scattering mechanisms are pretty clear. So what we discussed was parallel transport, electron transport parallel to the interface, parallel to your potential barrier. That's parallel transport. They are similar to your transport in bulk semiconductors, except the difference in your DOS function and scattering mechanism. And because of this reason, we studied the different scattering mechanism. The first scattering mechanism was your electron scattering mechanism, electron phonon scattering, right? So we studied what is phonon, how does the scattering occur, and what is the difference between the bulk. Three important points. And in impurity scattering, we considered mode structure and mode fed structures. So we just saw where is this impurity present, and what are the conditions, what are the assumptions we make to calculate the impurity scattering in mode fed. Two important things. And then we discuss the surface roughness scattering. Now how does this surface roughness scattering occur? What is the surface roughness in the case of a mode fed and MOS? Why in mode fed it is negligible, and why in MOS structures it is prominent? We saw that. And finally the inter-subband scattering due to the concentration of electrons. So for that we are considering a potential well to understand the concept. I hope these things are clear, right? So thank you. In the next session we will discuss the perpendicular transport and hot electron effect. Thank you. Have a great day.